welcome to another course on molecules, another lecture on molecules in motion. In this lecture, we are going to be discussing certain things which probably I have left out in previous discussions, but it is more probably most appropriate to discuss it now. We have discussed the measurement of transport number in the last two lectures, and we have introduced two methods of finding out the transport number of electrolyte, and that was done through the moving boundary method and the Hittorf's method. These are two experiments that have been used to determine the transport number of our electrolyte for a system where we want to find out what is the portion of the fraction of the current carried by the anion or the cation when a mole of electricity is passed through the cell. So, what we had talked about the moving boundary method and the Hittorf's method. Hittorf's method is one of the oldest method which is available to us, but it is more of hands on experiments which we need to do when we are talking about Hittorf's method. And here monitoring of the concentrations of each of the compartment has to be done for each of the electrolyte system and their electrode. This combination has to be used for any type of calculations that we want to know or when we want to find out. So, we do not have a formula to find out, but we have to understand the electrode reactions which is happening when the electrolysis happens in a cell. So, moving boundary method as of now, the Hittorf's method is sort of a little redundant, though it was one of the first pioneering methods put forward to understand that the fraction of current carried by the anion and the cation in a system is always a fraction of the total current which is passed through the cell. So, in the present context, the moving boundary method is considered to be more accurate in measurement for finding out the transference or the transport number. In addition, the equipment which we have for the moving boundary method is experimentally more easier to handle than the Hittorf's method. Now, saying that, let us see what are the drawbacks or what are the possible disadvantages we have for the moving boundary method. What happens when we are sending current through the moving boundary apparatus, then if you have excess of current, then if there is a current which is continuously passed, then you may generate a heating associated with passage of current. So, if you have heating, then you have convection currents generated in the electrolyte system that needs to be avoided because what you are monitoring here, you are monitoring a sharp boundary between the lead and the indicator solution. If the lead and the indicator solution does not have a sharp boundary generated, then you will have difficulty in reporting the transference number or transport number. So, what we need to take care, we have to take care of conditions which is not going to give rise to a diffusion in the sharp boundary between the lead and the indicator solution. So, what we need to avoid? We need to avoid the heating associated with the passage of current, which may generate convectional currents which can give rise to a diffusion in the sharp boundaries. However, the method is once it is established, the flow of current sharpens the boundary and makes the minor difficulty can be overcome. Then another point which needs to be taken into account when you are talking about the moving boundary, the relative concentration of the two electrolytes needs to be maintained, which is required for a sharp boundary. If you have a fast moving ion, for example, M in the discussion which we had, does not lead to any does not lead by more than a few atomic diameters, since the potential difference develops in such a tends to slow it down. In the steady state, the two ions will have the same velocity, but the M ion is always a little bit ahead of N. So, what we have to understand, the relative concentrations of the two electrolyte has to be maintained such that the boundary of the two solutions is sharp, because eventually the difference is only of because the fast moving ions may be whatever, maybe they are moving faster or slower. The difference in the lead solution and the indicator solution is probably in the order of few atomic diameters. So to have them very clearly generated, what you need to know, we need to maintain is a condition where the relative concentrations are appropriate in the lead and the indicator solution. Now, saying that those are the main two disadvantages of the moving boundary method. Now, what is the disadvantages of hit off? If I keep listing of them, then you probably will think hit off is one of the obviously not preferred method, but believe me, experiment wise hit off's method can be done in the lab much more easily. So, what happens in a hit off method? The concentration gradient by flow of current results in the diffusion of the electrolytes from more concentration to less concentration region. This leads to the to undo the effects to be measured, to minimize this diffusion, the experiment must be not extended over too long a time. Understood what I am trying to, we are having the electron move because of, this is not diffusion control. You are having the cations moving to the say the negative electrodes, and here movement of the ions is driven by the potential difference. Okay, it is not diffusion control process. But if you have too much concentration gradient, if you see what happens in that, you have accumulation of the copper 2 ion in the last lecture we had seen, and the copper 2 ions get accumulated in the cathode compartment. The concentration of the cation plus 2 copper is increasing, and here in the anode compartment you have a some amount of copper say dissolution of copper from the electrode to the solution is taking place. So, if you have accumulation of the charges, accumulation of the cations in any of the compartment, what will result? We have a diffusion of the electrolytes. The ion starts moving due to difference in the concentration, because if you have a concentration, then you will have a gradient in concentration, and that will drive for the ions to move from a more concentrated to a less concentrated region, and not entirely guided by the difference in potential across the two electrodes. So, to avoid this, what you have to do, we cannot make the experiment too long, so that if you are extending the experiment for too long, then you tend to see those effects more prominently. Again, if the time is too short, the concentration changes are too small and the current cannot be measured. A small amount cannot be used to determine the results. So, because we are talking about the moles of this cation and anion changing in each compartment, until you have sufficient amount of electricity passing, then until that is done, you cannot see the change, note the change, because the changes are going to be very small. So, what we have to do, we have to have a optimized amount of time spent for the current to pass, electricity to pass, so that we have sufficient amount to judge the concentration change and not excess, so that we have diffusion control current generated in the system. If large currents are used, heating effects occurs unevenly and produce convection in the solution. This mixes up the solution again. So, like in moving boundary method, here also we have to see that the large amount of currents which is used does not cause heating effect. If you have heating effect, then you have convection current and uneven current is accumulation of ions is going to take place, and this is going to give rise to the interference in the cell. In addition to this, the density difference that develops with the concentration difference between the parts of the solution may also produce convection. So, density difference means the concentration difference which is going to be arise in the different parts is also going to give rise to the diffusion control current. In spite of all of these difficulties, a reasonable good amount of measurements of the transparent number can be done by the Hittov's method, and a difficulty in interpretation arises because ions are all solvated and their mobilities and the motions in their motion they carry solvent from one compartment to the other. So, if you are going to go into a very detailed interpretation of what you are going to see, then you have to take the solvent effect. The ions are actually solvated when we are having in the motion. Now, when we talk about the solvated ion, what I have missed out in previous classes is to let you know about the Wardens Rule. What is the Wardens Rule? Wardens Rule, if you see the ionic mobility definition, it is the drift speed by the applied electric current, and from the derivation which we had used from Stokes law, and from there we had found out this expression of the ionic mobility, and the ionic molar ionic conductivity of the electrolyte was capital lambda, which was nothing but the ZUF. Z is the charge of the electrolyte, U is the ionic mobility, F is the Faraday constant. If you apply the value of U here from the expression, then you get something like this, but we know if we want to find out the molar conductivity of the electrolyte, it is nothing but the sum of the conductivities of the individual cation and the anion, and this should be multiplied by the formula unit amount of the cation generated for each type of electrolyte, plus and minus. So, if I can rewrite this, I can if you can see this, you can take the take out the common part which is going to be varying for a given solvent system. What is going to be same? This is the eta, it is eta is the viscosity of the solvent system, and Z is the charge of the electrolyte, E is the charge of the electronic charge, A is the the diameter of the cation or anion which we are looking into. So, if I can separate them out as to which are the things, if for a common solvent system what can happen, Faraday into E is the electronic charge that remains constant, 6 pi into eta, eta is the solvent system. If I can separate that out, then this can be represented something like this. Like if you have the contributions of the cation, then the amounts of the moles of the number of cations generated per formula unit of the electrolyte, that into the charge square of the electrolyte divided by the diameter diameter of the anion. So, similarly for the cation and similarly for the anion can be separated out by virtue of this. Only thing what we have seen is the square term of the Z if you compare these two. So, when you are having this, the only quantity on the right hand side depends on the medium. So, for a given ion in different solvent, we can write this is a constant, lambda into naught is a constant, which is the Wardens Rule. For if we want to find out for an infinite dilution where the concentrations approach when the concentrations are very low, then we can say the molar conductance of the at infinite dilution into the viscosity of the solvent should be a constant. So, what we have come out we come out with a fact that lambda into the viscosity coefficient of the solvent system, if we multiply, then it should be a constant. So, which side is this? Is the side which is dependent on the solvent system. So, for a given ion in different solvents, what we can have, if we have for a given ion in different solvent, the ions are the same, the solvents are, if the solvents are different, then we can say that it is nothing, because this is going to be lambda. What is the lambda? This is the lambda. This is the lambda. So, lambda expressions, if you can see, lambda expressions is, this is the lambda. So, this is entirely going to, this is the lambda part, and if the amount of this is changed, then what you get, if this is going to be fixed, then what you can get is lambda into eta naught is a constant for a system. It will depend on the medium. So, if you have different mediums, you will have different values of eta naught. So, eta naught into this is the solvent viscosity coefficient into the ionic mobility of the electrolyte system should be a constant. So, for infinite dilution, we can represent this by the alpha naught value, lambda naught value into the coefficient of viscosity of the solvent to be a constant. The Wardens rule is more accurate for large ions. If we compare the lambda naught into the eta naught value for a specified ions in different solvent, we will find we use different solvents and we are comparing the lambda naught into eta naught values for a specified type of ions for several different solvent. We will find that this product is a constant only for a large ions such as trimethyl ammonium ion, picric acid. For these, the consistency of this being a constant is very good. What we are looking into? We are trying to see the Wardens rule, which states the product of the lambda, which is the ionic conductivity, molar ionic conductivity at infinite dilution, into the viscosity coefficient of the solvent is constant. If we want to compare that for a very large ion, then what we can do, we take the specified ion in several different solvents and we see what is the product of lambda naught into the eta naught. The product for a very large ions such as the tetraammonium ion, this is the quaternary salt, and the picric ion, these are very large ions. For these, it has been found that the consistency of the product being a constant, this product being a constant is pretty good. If we exclude water, if we do not take water as the solvent, then the consistency of this product for electrolyte system is also fairly good for a small ion. Okay. So, if I say if we do not use water as the solvent medium, then the product of the lambda, that is molar ionic conductivity at infinite dilution, into the solvent viscosity for a small ion is also fairly consistent, perhaps within 20% of the average values. The difficulty in the small ions arise from the fact that ions are solvated. Okay. An ion is attached to the molecules of the solvent that are carried along with the ions as they move through the medium on the passage of electricity. The effective radius of the ion is therefore larger than the crystallographic radius that you can find for the cation or anion, and it is different for each type of solvent. The amount of solvent molecules that is held to the ion, the amount of solvent held to the ion is less with larger ions, since the electric field due to the ions itself is small. So, the effective radius is more nearly the same of the various solvents. So, Wardens rule is more accurate for large ions and for systems which is not water as a solvent. What happens if you have a small ions? The small ions will have a higher charge density sitting on them. If they are having larger charge density, as they move towards through the solution on the under the influence of electric field, then because of their charge density being higher on them, they tend to carry more number of solvent molecules along with them when they are passing through the solution. And if they are carrying more amounts of solvent molecules with them, then these are the solvated ions. The radius of the solvated ions is obviously going to be much larger when the ions are smaller, because of the charge density sitting on a small ion. Okay. So, the effective radius of the ions will be therefore much larger than whatever the expected crystallographic radius which we have reported in the books is going to be much compared to the crystallographic radius, it is going to be much higher, because now we are dealing with the solvated molecule, where the ion is actually having a sphere in which sphere around it, where you have the molecules of solvent associated with the anion or cation which is moving. So, the effective radius is nearly more to that of whatever we have obtained in a crystallographic measurement, will be more close to that of for a ion which is of larger size, and hence Wardens rule will be more accurate for the ions which are larger. Now, if water is included as the solvent under comparison, then what happens? The product of the ionic molar conductivity into the solvent viscosity coefficient is usually quite different from others, indicating a more marked solvation in water. Okay. If conductivities into water and H2O and D2O are compared, then what happens? The lambda into the eta naught, the solvent viscosity product, is nearly equal. So, what does that mean? If water is included in the solvent under comparison, this product is the product of ionic conductivity into the viscosity coefficient in water is usually quite different from the others, indicating more marked solvation in water. Okay. If I compare two types of solvents, and if we want to measure the conductivities and their take into account their viscosity coefficient of the solvent, if water is included as the solvent under comparison, the product of the lambda and eta naught is usually quite different from that of the other solvents. But if you have conductivities say in water and D2O compared, then the lambda into eta naught, that means the coefficient viscosity of the products, are nearly equal. So, what we have here discussed is the Wardens rule. Now, we are going to in the next class discuss how the concentration variation of when we are talking about molar concentration, molar conductivity, how this molar conductivity is dependent on the concentration of the electrolyte If you remember, according to Coloros's law, it is going to be dependent on the under root or square root of the molar concentration. So, in the next class, we are going to discuss what is the reason to have the conductivity or the molar conductance of electrolyte having a dependence of under root molar the square root of concentration of the electrolyte in terms of molar concentration. Why is it depend on under root C? Why is the molar conductivity or conductivity depend on under root C, where C is the molar concentration of the electrolyte. This is going to what we are going to establish using the and put forward the Onsager equation, which is the modified equation when we take into account what are the other contributions, and majorly there are two types of contributions which is going to retard the motion of the ions through the solution. So, instead of having ions moving through the solution, we have the here we have the ionic conductivities proportional to the under root of the concentration of the solvated ion. So, this relationship we will take up in the next class. Thank you.